Of Co Thoria ZSM 5 catalyst. It is a joint contribution from Grambling State University, Pennsylvania State University, and the U.S. Department of Energy. The authors are A.M. Murdy, A.A. Williams, R.T. Obermeyer, B.U.S. Rao, and R.J. Gormley. And the paper will be presented by Daya Rao.
This study is concerned with the kinetic and NMR studies of bifunctional Co Thoria ZSM 5 catalysts, and the work is a collaborative effort between Grambling State University, Dr. Murdy, who is with us here today, and Mr. Arthur Williams, Grambling State University, Louisiana, who did the NMR work. Myself and Bob Godley did the preparation of the catalysts and the catalytic activity studies, and Dick Obermeyer at the Pennsylvania State campus of McKeesport did the magnetic studies and also helped with the NMR. As you know, indirect liquefaction is concerned with converting coal to liquid hydrocarbons or oxygenated fuels through synthesis gas. After making synthesis gas, one can go directly to hydrocarbons through Fischer-Tropsch catalysis using a group 8 catalyst, or one can go to methanol, and using ZSM 5, one can go to high-octane gasoline. Our experiments were connected with combining the group 8 catalyst with ZSM 5 and trying to achieve a conversion to high-octane gasoline over a single catalyst from syngas. The reason for doing this is to try to circumvent the Schultz-Flory kinetics, which limits the amount of gasoline that one can get in the conversion of syngas to about 47%. Therefore, conventional FT processes are constrained by these maximum selectivities, and they are non-specific. So one way to bypass it is to add a zeolite such as ZSM 5 to the catalyst, so that the intermediates are siphoned off before they can grow to large molecules. And also the acid function of the ZSM 5 will provide aromatics, which will help in the octane rating of the gasoline. The studies we did were based on cobalt ZSM 5 catalysts promoted with Thoria. Here you see a number of catalysts containing cobalt and ZSM 5. The percent of cobalt in these catalysts is about 9 weight percent. And we added various amounts of Thoria ranging from 0 to 1.5 weight percent as a promoter. The experiments were done with hydrogen to CO ratio of 1 at a pressure of 21 atmospheres, 280 degrees C. What you see here is the CO conversion, and no Thoria is present. The CO conversion is 47% and hydrogen conversion is 78%. When you add a small amount of Thoria, you see there is a marked increase in both the CO and hydrogen conversion. But with further increase in thoria, there is not a big increase. Another big change that you find is in the reduction of the methane formation. This is the hydrocarbon product, C1 to C4 species here, and then C5 plus. You see when you add thoria that there is a reduction in the methane yield from 26 to 80% to 19 and so on to 16. And the gasoline yield, C5 plus, increases from 51 to 72%. And nearly 90% of the C5 plus is in the gasoline boiling range. Also, if you look at the percent aromatics, when there is no thoria, you have a very high percentage of aromatics in the product, nearly 50%. Then when you add thoria, this fraction goes down. And there are other interesting features in the product distribution that you see. There is a correlation between the amount of aromatics and the amount of light alkanes, especially propane and butane are also high. And when the percent aromatics goes down, these also go down. And we thought there is also a relation between the amount of C3 and C4 alkanes and the amount of methane, possibly through hydrogenalysis of the light alkanes. A mechanism that one can conceive for this correlation is the familiar mechanism given by Dejaev and collaborators. If you consider butene to be one of the primary Fischer-Tropsch products, then through acid catalyzed reaction, butene is polymerized to a branched form of octene, which then undergoes a hydride shift, giving a species such as this. These are all carbenium-ion interactions happening on CSM5, which also catalyzes the further reactions through cyclization and aromatization to give you, say, para-xylene. However, in this process, you will see that it has to lose 6 hydrogen atoms, and the hydrogen is then picked up by other olefins, especially the light alkenes, which are also in the product stream. They get hydrogenated to give you the light paraffins. And that is the reason why when you find a large fraction of aromatics in the product, you also find a relatively large fraction of light alkanes in the product. And our next postulate was that these light alkanes undergo hydrogenolysis on the cobalt in spite of the fact that there is considerable amount of CO around and give you additional methane. Now, we wanted to see if we can understand the promotional effect of thoria by doing NMR studies. Now, the promotional effect of thoria is not totally understood, but one suggested explanation goes as follows. Since thoria is a basic oxide, it would donate electrons to the metal, thus enhancing CO chemisorption while weakening that of hydrogen. Then the chemisorbed CO would experience a strong metal-carbon bond and a weaker CO bond because of back donation of electrons to the vacant anti-bonding 2pi star orbitals of CO. Now, if this were true, it should be reflected in some of the NMR properties. For example, the surface cobalt atoms, which might pick up a fraction of an electron, say from an adsorbed CO, might show a slight shift in the resonance frequency in zero-field NMR. Similarly, if one could perform the NMR of C13 over cobalt and compare the frequency with C30O over cobalt thoria, one might see shifts due to the increased bonding between the metal atom and C13. Now, in the case of cobalt, since it is ferromagnetic, you cannot do a straightforward NMR. But what you do is to do the NMR of cobalt in its own magnetic field. It's similar to a Mossbauer experiment in iron, where you see the six-finger pattern splitting because of the internal field of iron. Now, cobalt has a similar internal field. The hyperfine field is about 300 kilovolts, and you can get the NMR of cobalt in its own field around 200 megacycles. And if there are slight changes in the magnetic moment of the cobalt, one may be able to see shapes or broadening of the cobalt line. The experimental setup is a relatively simple one because you don't have to use an electromagnet. It was originally designed to do NQR experiments, nuclear quadrupole resonance measurements, where you do not need an external field. The electric field gradient at a non-cubic site for nuclei such as chlorine or bromine will split its nuclear levels, and you can induce transitions with an RF field. The modifications that were made was to replace the Zeeman, the spelling error here, it should be a Zeeman coil, which provides an audio modulation of the, to get the, enhance the signal and to do some amplification through phase sensitive detection. Now this was replaced by a vibrating capacitor in its neighborhood as shown. In this particular case, you have the RF tank coil in which you place the specimen, and then there is attached to it a vibrating capacitor which will do a frequency modulation, and this will help the phase sensitive detection. So what one does is to keep the sample and gradually scan the NMR frequency over the given range and try to see the resonance. Okay, we studied several samples here. Cobalt physically admixed with ZSM5 with different amounts of cobalt 3, 6, and 9, and then cobalt Thoria. Now, for comparison, we have taken a cobalt powder straight from the bottle. Now, as you know, cobalt has two crystalline forms, FCC and HCP, and these occur at different frequencies. The FCC form gives you a resonance around 213 megahertz, and the HCP form gives you a signal near 221 megahertz. Now, most samples of cobalt will have both of these allotropic forms. In addition, the FCC form also has additional lines due to stacking faults, and this perturbs the frequency from the central FCC frequency, and so quite often you see the fault lines as well. Now, in the samples that we use, the cobalt ZSM5 samples, you could see that the intensities of the FCC and HCP lines were almost about the same order of magnitude. However, when you added Thoria, you found mostly the FCC line, and we could not see any HCP line right after reduction in hydrogen at 350C. Now, one of the effects of Thoria is to decrease the particle size. These samples here without Thoria had an average crystallite size of about 40 nanometers, and the ones containing Thoria had an average particle size of 10 nanometers. So one of the effects of Thoria is to prevent sintering during the reduction in hydrogen. Thoria being an oxide which prevents sintering. It's one of the functions is believed to be to reduce the particle size of cobalt. Now what happens is when the particle size goes down from say 40 nanometers to 10 nanometers, you have the cobalt particles reduced to now single domain particles. In zero field resonance, which is occurring in a ferromagnetic sample, in a ferromagnetic sample you have what are known as domain walls. You have ferromagnetic domains where the spins in one domain are oriented in one direction, and in the neighboring domain the spins are aligned in a different direction, and in between them you have a domain wall where the spins gradually turn over. Now when you apply an RF field, such a domain wall also vibrates with the frequency of the RF, and this causes an amplification of the RF field and gives you a strong signal. Now when you go down to small particle size as in cobalt thoria, you almost are reduced to single domain particles. The typical magnetic domain size of cobalt is about 100 angstroms, so you are down to single domain particle size, and therefore the number of domain walls is considerably reduced, and this results in a reduction in the intensity, NMR intensity. Now, the amounts of FCC and HCP phases that are actually present are not entirely proportional to the signal intensities that you see here because of complications caused by the quadrupole interaction with cobalt. The intensity of an HCP cobalt resonance is about 20% of that of an equal volume of face-centered cubic cobalt. The reason being that the HCP resonance derives from the interaction of the nuclear quadrupole moment of the cobalt-59 nucleus, which has a spin of 7.5, and therefore the NMR line is now split into a central line and also some satellites, and you only are measuring the intensity of the central line, and therefore the intensity is much less than an equal number of nuclei of FCC cobalt. So while you have to use this normalization factor when you convert the line intensities to actual amounts of HCP and FCC phases. Now, these samples were used in syngas conversion at 280 degrees for 48 hours, and the spectra were again studied. One thing we found was a somewhat of an increase in the intensities of the 3% and 6% cobalt, but the 9% cobalt did not show an increase. It actually showed a decrease in the line intensities. In the case of the cobalt thoria samples, if you remember the previous spectrum, there were no HCP lines, but after being used as a catalyst, the HCP lines started appearing. There was again a reduction in the intensities of the FCC lines in the case of the cobalt thoria, 3% and 6% samples, but there was an increase in the 9% samples. Now, these line intensities are related to several factors. Some of this is due to partial oxidation of the cobalt because of the prevailing water that is present during FT synthesis. Now, the increase in intensities when they occur can be, especially in this case, can be related to the sintering of the cobalt particles from, say, the 100 angstrom particle size to about 400 angstrom particle size during the reaction itself, and this might lead to increase in the particle size. Now, our original aim was to look at shifts in cobalt frequency because of thoria addition, but it turned out that the line widths were about 0.3 megacycles, and we could not really tell whether there was a shift in the NMR frequency of cobalt because of the addition of thoria. Again, we also studied cobalt ZSM5 catalysts with cobalt impregnated on ZSM5 instead of being physically admixed. then cobalt was added in two different forms, the aqueous impregnated and the acetone impregnated samples. And again, all these gave lysine positions that were formed in the cobalt powder with both the FCC and the HCP and the fault lines appearing. So in conclusion, we say that the promoter Thoria seems to inhibit particle growth and crystal faulting and favors the growth of the FCC phase as well as the growth of single domain particles of cobalt. Then use of the material as a catalyst in syngas conversion tends to cause sintering of single domain species to that's a mistake there, it should be multi-domain species, as well as a highly faulted crystal structure. Now the NMR spectrum of the reduced cobalt catalyst prior to its use is a combination of FCC and HCP phases for the unpromoted samples, and only the FCC phase for the promoted samples. So obviously the presence of Thoria is inhibiting the formation of HCP phase. However, spectra of both phases are present after the samples have been used for the catalytic conversion of syngas. Now, we have not done any C13 NMR work as yet. This could be a very difficult experiment because of the small number of C13 that are available. One would have to use liquid helium temperatures in order to enhance the NMR signal. But we are going to make these attempts on both cobalt and cobalt Thoria. And if we are able to get the C13 NMR, we hope that we will show some real effects due to the promoter Thoria. Thank you for your attention.
Any questions? Yes.
Two questions. This is Cal Bartholomew, BYU. The first, your data deals with Anderson-Schultz fluorine. Do these product distributions for the cobalt ZSM5 follow the Anderson-Schultz fluorine? And I guess related to that, are the cobalt crystallites in or out of the pores?
Oh, well, they do not follow Anderson-Schultz fluorine because of several secondary reactions that occur, and also because there is a cutoff near C10 or C11 in the product distribution. And as I mentioned, there are secondary reactions which give you anomalous increases in C3 and C4 alkanes. So the distributions are not at all Anderson-Schultz fluorine.
But not necessarily a shape selective effect so much as a result of secondary reactions.
That is correct, yes.
Okay.
Of course, the cobalt is not within the pores of the zeolite. As you know, ZSM5 pore size is only 5.5 angstrom. And we are dealing with cobalt metal particle sizes in the range of 100 to 400 angstroms.
So they're clearly excluded from the
Yes.
The other question dealt with the comment that you made that you thought Thoria would have the effect of increasing CO chem absorption strength and decreasing hydrogen. It seems to me that if that were the case, since CO, the reaction kinetics for CO hydrogenation on cobalt involved CO to the negative power and hydrogen to the positive power. At least that's what we found in our kinetic studies. This would suggest that you would have a significant decrease in the rate of reaction. Now, of course, you would have, as you pointed out, an decrease in particle size and increase in surface area to counteract that. But I wondered if you had looked at the kinetics of the reaction and what comment you would have regarding the kinetics of it.
Oh, well, our measurements were at 20 atmospheres We do find that addition of Thoria causes an increase in both CO and hydrogen conversion. But now we are working at 50 to 80% conversion ranges, and it's somewhat difficult to compare with, say, your results, which would be more differential conditions. And
So you think the kinetics might be different?
yes.
John Eckert, UT Austin. I had a question. When you added the Thoria, there were significant changes in the distribution and the conversion, and you added Thoria up to fairly high extents. Where is the Thoria in the zeolite? And the second question is what happens if you study this catalyst without cobalt, just Thoria?
Okay, we added relatively small amounts of thorium. Typically, if we had, say, 6% cobalt, we would have about 0.58% thorium. Now, well, let me go back and describe how the catalysts were made. It was cobalt thoria was co-precipitated and then physically admixed with ZSM5 and then reduced. So you would not expect thoria to be inside the ZSM5. However, after reduction, we did some IR studies, and we found that the brown-stick acid strength was reduced, the intensity of the OH acid line, and we presumed that this happened especially for the cobalt thoria. It didn't happen for the cobalt ZSM5 samples. So we think that under the reduction conditions, somehow there is a solid state migration of thoria into the exchangeable sites, and this could be partially reducing the acid strength of the zeolite. So there is a partial penetration of thoria apparently into ZSM5. Now, where the rest of the thoria is, we do not really know. We think because of the promotional effects that we found on cobalt, both the particle size reduction and the change in product distribution, we think it is somehow intimately associated with cobalt, but how exactly it is, we do not know. Now, the other question was whether we studied Thoria ZSM5. We did not. Now, highly dispersed thoria has been shown by Coleman and others at the Lawrence Livermore lab to be very highly selective to methanol, not necessarily at these temperatures of 280, but I think they worked at somewhat higher temperatures, treasures. So if Thoria ZSM5 was examined under those conditions, probably it would be very selective to gasoline because you would be eliminating the methane formation, even the small amount of methane that we are observing. So that would be a useful thing to study, but we have not done it.
Okay, one last question.
The University of New Mexico. You're dealing with fairly large particles, so you should be able to get other structural information about them, like X-ray diffraction. Do you get any information that corroborates the findings from NMR?
Yes, we have done the X-ray line broadening studies, and you can measure the particle size for relatively small cobalt around 100 angstroms. But once you have particle size of 400 nanometers, the broadening is not present and becomes insensitive. But for particle size less than 100 angstroms, what we derive from NMR tallies with what was observed from X-ray line broadening.
I'd like to ask one last question. There appear to be some changes in the frequency of the signal by the NMR. Are these shifts significant, or are they experimental error? And if they are significant, are they due to electronic changes of the cobalt?
Well, our accuracy of measurement is about plus minus 0.2 megacycles in a frequency of 200 megacycles. So those are the errors of measurement. Now, the lines were broad. That was the real problem, about a megacycle or so broad, and it was kind of difficult to pinpoint the center. So in future experiments, what we would want to do is to have a sample which gives a very sharp nuclear particle resonance line, like an iodine, in arsenic triiodide or something like that. So that will act as a frequency marker, and then we hope that we'll be able to see if there is a difference between, say, cobalt resonance and a cobalt Thoria resonance, and we should be able to tell if there is a promotional effect.
Well, this will conclude our today's session on CO hydrogenation. There will be another session tomorrow, and I would like to give a hand to all the speakers and thank them for their contribution today.